Please note, the first page there asks you for your signature. Please sign it. Tear the 2 pages apart. You keep the second one. I get the first one back. Why? So that I have proof I gave it to you. Because what's on that second page is information for you. The original idea is that this would say, hey, here's where we are in terms of what you remember and what I think is good material to have in your head to move forward with. Here's the bad part. This was a disaster. This was my first time giving this assessment. These questions came from my algebra final exam. So if you'd taken my algebra class last year, these questions, or ones very similar to them, would have been on the final exam. Ow. However, my recommendation to all of you at this point is for you to say, all right, if I want to continue in this course and move forward in trigonometry, I need to do 2 things. The first of which is to remember all the stuff that leaked out of my brains over the summer as I sat on the beach with a margarita. I understand it was a great summer for me too. I was in Kentucky for 2 weeks and there was bourbon in everything. I went to a conference and I kid you not, the popcorn had bourbon. I don't understand these people. I tried to be sober, really, I did. However, the 2 things, I got to remember, I got to bring that stuff back. If it's been a while, if it's unfamiliar, I need to go camp out in the Math Enrichment Center over in Reeves. I need to meet with Ms. Benanati or any of the tutors for this course or for algebra to bring my skills back up. And then to stay on top of this material. And that's the hardest part. Because what I'm going to talk about today, the new material on exponential equations, is stuff you may have seen before, and it's somewhere back there, hiding behind K-pop Demon Hunters, maybe? I don't know. It's way back there. We need to find it, pull it out, and say, I know how to do this, but stuff's not due until Monday. And if stuff's not due until Monday, you could say to yourself, I can spend the weekend on it. And then it's Sunday night at 10:30 p.m. and you're going, oh, this is due in 11 hours. And that means time management. That's different. So, you have a choice to make. It is possible there is an algebra class at this time. If you are like, I'm going to die, I don't want to do this, you are welcome to transfer the algebra class. Information is on that second page on how to talk to the registrar's office to rearrange your schedule to make that happen. There aren't a whole lot of seats in there at this point. I think there are a dozen. You're welcome to make that transfer. I think this is a matter of being out of practice, not a matter of I've never seen this before. And if that's the case, it's going to be a sprint at the beginning. So gird your proverbial loins. We're going to hit the ground running. Meanwhile, sign that first page, send it this way into the middle, and I will collect them coming up either side. An additional aside, no one except me will ever see those placement exams. So your written work will stay with me in my office. Summaries will be discussed among the math program and the dean of the school and probably the provost, but that's, summative data. No names get attached to any of that shit. So if you're embarrassed or worried about that, no, nobody will see that but me. You're good. I will probably have forgotten what you wrote specifically already. Okay. When I teach algebra, the most common issues show up in discussions not of polynomial behavior. Most people seem to get that, okay, it's exponentials and their dreaded friend logarithms, which got everybody. Best part, it's just powers again, just dealt with differently. Y equals x squared is a quadratic equation. And that means that that x can take on any number we're going to use. No, that didn't work. Let's fix that. There. X can change as much as we want, but that 2 stays the same. Take any number, multiply it by itself. -3 quantity squared is +9. I'm good to go. I want to switch those around and deal with a power that varies. So now as I pick the x, I take 2 and I raise it to that power. Well, x is 1, 2, 3, 2 to the first, 2 to the second, 2 cubed, 2 to the fourth, 2 to the fifth, 2 to the -1. What do negative powers do? Raise something to a negative power. See people gesturing and everybody's terrified. I promise I won't laugh. The only stupid question is, do I need to breathe? And if you ask it, the answer is no. Yes. They made the reciprocal, the inverse. So 2 to the -1 is 1 over 2 to the 1, which becomes 1/2. And 2 to the -2, 1 over 2 squared, 1/4. I skipped one. We think about this as multiplication. Powers are repeated multiplication. So what does it mean to multiply something by itself? No times. Yes, ma'am. Yeah, here. What does it mean when I do 2 to the 0th? This is one of those, I know I've seen it before. Where is it? It is 1. How many 2's does it take to make up a 1? None of them. Okay. But here's a slight problem. This chart has as its x values nice numbers. But x can be any number. Well, crap. Fractional powers? It means to take a half power of something. Which root? The square root, because a 2 is a square. 1/2 is the reciprocal of 2, so it should undo what 2 does. 2 squared things, 1/2 will square root things. Now I deliberately put extra numbers in there. You don't normally write that little 2 by the notch in the root because everybody assumes that a root means a square root. And I wrote the 2 to the first because the numerator of this fraction is a 1. It turns out, if I have any fraction, I do this same thing. I take the root that goes with the denominator of the base, that 2, to whatever power. By the way, I can do those in either order. I can do the m part on the inside or on the outside. Because I'm repeatedly taking powers, it doesn't matter which order I do them in. So I can do x is a half. I can do x is 3.7 if I think of it as 37 over 10. I can do 2 to the 14 over 3 if I needed to. I promise there are times when I actually do need to, and we'll find them. This also means that I can now do powers that are weird numbers. I could do 2 to the pi. Well, because pi is 3.14159, right? All of that stuff. So I can take 3, and then I can take 3.1 as 31 over 10. I can take 3.14 as 314 over 100. 3.141 is 3141 over 1,000. And I can look at what happens as I put more and more decimal places. Ideally, and this is a calculus idea we'll get to later, these converge, close in on a particular value, rather than just blowing off to some weird ass infinity. And as long as that happens and we get a nice result by looking at that list of numbers, then I can say that's a working value. And it turns out that I can do this idea not just for 2, but for almost any number I want. A function of the form b raised to a power, b to the x, is called an exponential function with base b. I want this to work. So let me think about this root again for a second here. Where does a square root go? You can't do that. What makes a square root break? Negatives. I can't take the square root of a negative. So if I want to make sure that these rules work, I need to never let b be negative. Now, why didn't I allow 0? What's 0 raised to any power you want? 0 times 0 times 0 times 0 is 0, right? The only place I'm going to get that weirded out is if I do 0 to the 0, and that doesn't make sense because it should be 1, it should be 0, it should be 1, it should be 0. It's kind of two things at the same time. I'm not going to deal with it. So I didn't want to use 0. On the other hand, 1 raised to any power is just 1. No matter what I do. That's boring. So we'll omit that one. And that means that we can actually think about the behavior of these graphs and the functions in 2 groups. The ones where the base is between 0 and 1, and the ones where the base is between 1 and anything else. Grab your graphing calculator if it's working. If it's not, grab your iPad and go to desmos.com. go to your computer, desmos.com. Grab your phone. We can use that too. If you've got a graphic device, this is the place to use it. Ideally, at some point, you will have one of these that works. Okay. We're going to do two separate groups. We're going to do the group from 1 on to however big we want. We're going to do the group from 0 to 1. So I'm just going to go to the y equals menu. And I'm going to put in 2 raised to the x power. The raise is that shift 6 caret. If you're in Desmos, you can enter it the same way. 2 to the x. Older programming languages used to use the multiplication symbol twice. So it'd be 2 star x. They got rid of that in Fortran, I believe. So that's 1970 something. All right. I want to do numbers that are bigger than 1. 2 is a nice place to start. But let's add some others. Let's do 5 to the x and 10 to the x and also 1.1 to the x. I want you to graph these on the same window. All 4 of them will show up. Right now, they're all highlighted in my calculator. If you are using Desmos, you'll have to enter them on the same sequence set. I think it's on the same line. You separate them by commas and they all show on the same graph. I don't use Desmos very often. I'm going to set the window on my calculator to go from -5 to 5 in the x direction. And if I go back and I look at that table that we made for 2 to the x, I notice that all of those numbers were positive. So my y values don't need to be negative to see everything in that 2 to the x graph. I want to actually see the axis, so I'm going to make sure I show some negative numbers just to see that. But now that I've got this, if I hit the graph button, it'll show me 4 pictures. 2 to the x, 5 to the x, 10 to the x, 1.1 to the x. All right, wait a second. Wait a second. Trace. That first graph is 2 to the x. See my little blinking spider? That's our graph for 2 to the x. This is where if you have a color version, they'll be in 4 different colors. You'll be able to tell them apart better than I can. That's 2 to the x. If I put in an x value, like 2, that matches our table, doesn't it? 3, -2, 0, went through 0, 1. This is the correct picture. 5 to the x, 10 to the x, 1.1 to the x. Zoom out. Two to the x, 5 to the x. It's kind of really getting steep there in the middle, 1.1 to the x. Ah, there it is. But wait a minute. It's doing that same curve as well. What's the difference between these 4 pictures? Or what's the same? They all go through the point 0, 1. And as the number we are dealing with gets bigger, the graph gets steeper. It gets closer to the x-axis on the left and steeper closer to the y on the right. Even that 1.1 to the x is eventually, if I zoom out far enough, going to look like this. They're all going to look like this sweep, going from really close to the x-axis on the left, blowing up on the right. That makes that left half of the x-axis something. We gave a name to this idea. I can get really, really close to this line, but I'm never going to touch it. I'm never going to cross it. An asymptote. The root of asymptote is the word symp, S-Y-M-P, like sympathy. To feel close to something, to feel with it. It's like being with your significant other in your parents' living room. You can get as close as you want, no touching. They all blow up on this other side. I can put in any number I want. This graph has no holes in it, no jumps, no weirdness. It's smooth all the way across. So the domain, the numbers that are allowed in, goes from minus infinity to infinity. But it always spits out a number bigger than 0, because I'm never going to cross this x-axis. The closer my base is to 1, the shallower this graph gets. If I did 1.01 to the x, it would look like a straight line. It would be growing really, really slowly. Questions? So if I go back and just look at 2 to the x for a second, I notice something else really nice about this graph. If I draw a horizontal line anywhere on this picture, how many times will it cross the graph I'm interested in? Once, and only once, right? If you draw a horizontal line across this, no matter where you draw it, it only cuts through once. Even when you're way down here, it's kind of hard to see, but that graph is still tilted, so it only touches it once. That means this function is 1 to 1. It passes the horizontal line test. Long time ago, I know I heard that phrase. Okay. What happens if I change the base? Instead of being bigger than 1, I want to be between 0 and 1. There's 1/2 to the x. I used 0.5. I'll do 0.75 to the x. 0.1 to the x. We'll just get 3 of them to look at for now. And lo and behold, picture turns around. And now that asymptote is on the right instead of the left. It's still going through 0, 1. They all go through that same point. And the closer we are to 1, the flatter it gets. .75 is the low one. 0.1 to the x is the high one. Just like with the growing ones, as we go from left to right, the closer we get to 1, the flatter it is. The further we are from 1, the steeper it is. Only now, further from 1 means closer to 0. It's an exact mirror image. There's 1/2 to the x. There's 2 to the x. Why are they the exact mirror images of each other? Look back at the table that we made for 2 to the x. The answer is there. Say again? Almost. But the distance from 0, if I'm 2 on the right in this graph, if x is 2 on the one that's going up, I'm at 4. If x is -2, I'm at 1/4.
So it's inverse.
The negative power makes it 1 over, doesn't it? So when I do 1/2 squared, that's the same as 1 over 2 squared, which is 2 to the -2. This spot here is the same as that spot there. It's the 1/2 versus the 2 that gives me that equal distance from 0. Hot damn. So these graphs flip. If you know what's going on with 2 to the x, you know exactly what's going on with 1/2 to the x. You just turn around. These are on page 380 in the text. There's a box with a description of all sorts of things about these graphs. Questions? Talk to me. Again, a lot of times when we talk about functions, we talk about changing them, about moving them, squeezing them, and stretching them, and all that sort of crap. Transformations. I'm going to stick with this graph of 2 to the x. What changes? Well, yeah, okay, so what does that +4 do to my picture?
I like 0.
Almost. It's going to change my y-intercept. Yeah, but what is that?
On the x-axis.
Instead of being on the x-axis, where am I going to be?
Y-axis.
If I actually move on the y-axis, that's going to change something really weird. I'm going to move up by 4. It's going to change my y-intercept. It's going to move it from wherever it was up 4. But it's going to do that for everything, which means it's going to move the asymptote. Instead of it being the x-axis, which is at a height of 0, it's now at a height of 4. Which means I know exactly what this picture looks like. Just take the old picture and shove it up, right? Ta-da! I didn't need the calculator for it because I knew what the picture looked like. I wrote it weird on purpose. What happens with this one? Same picture, just dragged downward instead of put upward. The parentheses are unnecessary, but I don't have lines on this paper. So keeping track of what's in the exponent and what isn't is a little more difficult. I try and put the parentheses just to make it clearer. What's going to happen here? Okay, wait a second. Go back to the table that we made. If I put in x equals 0, what's going to happen in this exponent?
Gonna be a 1. What's the negative, so it's gonna be the inverse.
So it'll be 2 to the negative 1, right? And if I put in a 1, that's going to give me 2 to the 0. And if I put in a 2, that's really going to give me 2 to the 1. So everything seems to be happening one step off in the x direction. So what was going to happen at 0 now happens at 1. And what was going to happen at 1 now happens at 2. And what was going to happen at 2 now happens. We've taken the picture and we've moved it to the right 1 unit. So what I was thinking of is my y-intercept, 0, 1, is now over here at 1, 1. Because when I put in x equals 1, I get 2 to the 0 power. Now my first reaction is, wait a second. When I added, things went up, because up is the positive direction. When I subtracted, things went down. Down is the positive direction. I'm subtracting, why am I going right? That seems ass backwards. It is. Because what I'm really doing is I'm moving the axis to the left. Sneaky mother, how dare you? We really refer to this as frame shifting. You won't ever hear that term again. So here's an interesting comment. Notice where the addition is or subtraction is taking place. If it's on the outside of the 2 to the x or of any function, we move up or down based on the sign. Up when it's positive, down when it's negative. But when we're doing it on the inside, I need to change what was plus to a minus. So where's that graph going to shift? To the left by 3, because I think of this as 2 to the x minus negative 3. When I'm on the inside, I want to think of subtracting. You did this. The vertex of a parabola, HK. Maybe. Some of you are like, in there. One more. Actually, I'm going to split it up. It'll be 2 more. What does that minus sign do? All of my positive numbers now become negative numbers. I flipped it over. That's because I'm multiplying by a minus rather than adding or subtracting. I'm multiplying this time. I could even go further and multiply not just by -1, but by any number. What does multiplying do to a picture? No, my y-axis motion is going to be like my left and right. It's going to happen on the inside, not the outside. That's next. If I take a number and I multiply by 2, right? Everything gets twice as big, right? But if I have 0, what's 2 times 0? So it doesn't move. But everything above it moves. And everything below it moves. When I multiply by 5, I take that graph and I stretch it to be 5 times taller. If I take that graph and I multiply by -3, I flip it over and I make it 3 times taller. If I multiply by a third, squish. Now, at this point, my brain reminds me that when I went from 2 to the x to 5 to the x to 10 to the x, the graph looked the same, it just got stretched. There should be a way to turn one graph into another. There is, I promise we'll get there. It's just not. If I want to flip left to right, instead of working outside the 2 to the x, I work inside it. That flips me across the y-axis. Now I am sure that this is about as clear as mud at the moment. A recommendation. Take 2 to the x and then mess with all of these numbers. Put something out front. Put a plus or a minus inside. Put a plus or a minus outside. And draw the picture and see what happens. Questions? Exponential functions grow fast. There is a story. I think it's originally Persian, but I'm not sure. The game of chess is a war game. You have your army, they have their army, you have rigid moves, and you try to defeat your opponent to cause them to surrender. It's a war game. But chess was developed in Persia. By the way, the bishop in chess with its diagonal motion is actually from the English version of the game about 300 years later. That piece was originally an elephant. And those 2 lines on the side of the bishop that to us look like it should move diagonally, those are elephant tusks. The game is played on an 8x8 grid. So the chessboard has 64 squares. The ruler, don't know the appropriate term, Shah, whoever, in Persia was so impressed that he said, I want to reward you for bringing me this game. What can I give you? And the man said, I would like grain to be able to sow fields and to feed my family from here out. Let us put 1 grain on the first square, and 2 on the next, and 4 on the square after that, and 8 on the square after that. And if we can finish this pattern on the chessboard, that would be my requested reward. After thinking for a minute, the head accountant, the vizier, came over to the king and said, we got a problem. How many squares on the chessboard? Grab your calculators. 2 to the 64th. 1.8 times 10 to the 19th. 10 to the 6th is million. 10 to the 9th is billion. 10 to the 12th is trillion. 10 to the 19th is 10 million billion grains. He wanted the entire output of Persia's grain facilities for the next 10,000 years. This is more dollars, more pennies than the entire output of this country in its entire history. That's huge. These grow so fast, so quickly. They are the fastest types of functions we can draw. So why do we use these functions? Anybody here have a credit card? Your credit card charges you interest. What's interest? Theft, damn it, it's my money. No. The credit card loans you money, and they say, well, you have to pay for the privilege of using my money. And interest is calculated by taking the amount you borrowed, the principal, multiplying by the rate at which you borrow it, say 7% or something, and then multiplying by the amount of time you have that money. Say I borrowed it for a year or 3 months or whatever it is. I need all of those things put together, and that's how much extra I owe back. So I owe that, plus I owe the original, right? So the total future amount that I owe is the interest plus the principal. I didn't make the formula up. Now, when I think of interest this rate, this is called simple interest. I just calculate it once. You're going to borrow this money for 3 months, $1,000 for 3 months at 6%. I calculate it out. In 3 months, you owe me this much. And off we go. But my bank works the same way. If I put money in the bank, they can loan it to people. They have to pay me for the privilege of using my money. So I'm going to stick into the bank $1,000. And the account I put it in pays me 5% every year. So January 1st, throw $1,000 in the bank. They get to use it for whatever they want. At the end of the year, they owe me $50. 0.05, 5% out of 100 times 1 year. So how much is in my account? Hey, wait a minute, there's 1,000 in both of these. Let me factor that out. $1,050. That's the $50 they gave me. I don't need that $1,000 right now. I'm going to leave it there. What happens at the end of year 2? I get another 5%, right? But I get 5% on this money, not on $1,000, because they've had this extra $50 to play with too. So at the end of year 2, it's 1,050 plus 1,050, 0.051. Now, wait a second. Again, I'll factor this out. I multiplied again. That 1050 came from that top line. This is the same as 1000 times 1.05 times another 1.05. It's an exponent. If I want to know how much is going to be at the end of any year, I can put in whatever power I want, which means I could do a year and a half or 3 years and 9 months, and I could use one of these fractional powers that we were just looking at, couldn't I? Interest is an exponential function. That 1.1 to the x was money growing at 10% interest. Questions? We can generalize this for any bank account I want. This is interest paid more than once a year. What if my interest is paid every 3 months? Well, then I would do it 4 times a year. So I take that 5%, I divide it by 4, but then I take my number of years and multiply it by 4. So I'm doing it every 3 months instead of once a year. I am going to give you a golden opportunity to invest in the Bank of Sassmore. There's a rule, though. You are only allowed to invest $1. I pay 100% interest. You are only allowed to invest for 1 year. So when I do this in the Bank of Sassmore, it looks like this. $1, 100% interest for 1 year. I didn't specify M, did I? How often do you want to calculate your interest? If you only do it once a year, then at the end of the year, you get $2. But if you do it 4 times a year, then at the end of the year, you end up with $2.57. What if you did it more? No matter how big you make M, this number gets closer and closer to E. That's my favorite base in the entire world. If you want to do exponential functions, the base I'm going to choose almost all the time is E. 2.71828182885. It's an irrational number, but it's between 2 and 3. That's the base I'm going to use the most often. Please read through the examples using base E in chapter 4, section 2. There are only a couple of them, and we have covered both 4.1 and 4.2. I will see you all on Friday. Have a wonderful rest of your day. If you want to talk to me about that placement instrument, please feel free. I will be in my office hours over in the Enrichment Center later today. Have a wonderful rest of your day.
Sorry, last night, so